All right, we're looking at solving nonlinear systems, right? We looked at linear systems earlier in the year. Now we're looking at some systems. And what's a system? It's just a collection of more than one equation. We're looking at some two-dimensional systems where we have two unknowns, and but they're not linear. Some of these are quadratic, and I don't think anything's going to be bigger than a linear quadratic system. Let's just talk about how we could solve these things. And there's really nothing here that you don't already know theoretically how to do. It's just a matter of seeing the tricks and getting a little practice. Okay? So what are some suggestions on this one? What could we do here to solve this? There you go. So we're going to solve by substitution, aren't we? Right? We've got a substitution equation already served up to us here. We've already got this top equation solved for y, and so it's ready to substitute, isn't it? Remember what we always want to do when we identify a substitution equation, put a box around it, because you're probably going to come back to it, right? We're solving this. What's our solution going to look like? When you write the answer down, what's that going to look like? What do you think? How many variables are there? It's going to be one or more ordered pairs, isn't it? Right? Because we're going to need values of x and y. What would that correspond to graphically, those ordered pairs? Like if I were going to graph this system, what would the ordered pairs correspond to on the graph? X-intercepts? No?
Be where the two lines touch.
They're intersections of the graphs. Everybody see that? Okay. Because these are not linear, this is a parabola, isn't it? Right? And that's a line. We have the possibility of having not just a single intersection now. We have the possibility of having two intersections, right? Okay. Okay, so let's do this then. If I make that substitution, what are we going to get? So this equation is then going to become 3x minus 2 times y. So everything, we're going to replace the y with the quantity 1/4 times x minus 3 quantity squared. And all of that is equal to 13. And now we're just doing algebra, right? What do we do next here? What do you think? Okay, is there anything, we got to simplify some things, don't we? So I've got 3x minus 2 times 1/4 times x minus 3 quantity squared, right? So look here, I've got a product. Do I distribute this? It's not even really distribution, is it? I've really just got three things multiplied together. I've got a negative 2 times a 1/4 times this quantity squared. I multiply things in pairs, right? So which two factors should I multiply first, probably? Maybe those two, right? What's negative 2 times 1/4? That's just negative 1/2. So we end up with 3x minus 1/2 times the quantity x minus 3 squared equals 13. 1/2 times something is the very same thing as that something divided by 2, isn't it? Right? So if I wanted to, it's your choice. I could write this as 3x minus the quantity x minus 3 squared over 2 equals 13 also, right? Okay, what do you think? This is really good practice. Where I'm throwing something at you here. You just got to think algebraically on this. Is there one right way to do this? No. but there's a good way to do it. There's probably a better way to do it. What do you think next? Any suggestion? What's ugly about that equation? We got a fraction, right? We'd rather not have to do a bunch of algebra and arithmetic with fractions. So is there a way we could get rid of that fraction? Okay, good. I could distribute a 2 through, couldn't I? How come I can distribute a 2? Well, because really I've just got 3 terms up here total, don't I? I've got this term, and then 1 term on the other side. When I have a bunch of terms that are just added or subtracted, that's when I can clear fractions, right? I can just distribute a 2 through. And what's going to happen if I distribute a 2 through? Let's just use this bottom one down here. Not that it matters. Either one of these would be fine. If I distribute a 2 through there, what am I going to get? Okay, so I'm going to get a 6x when I go there. What about there? Okay, minus the quantity x minus 3 squared equals 26. Okay, good. All right, now what? Now we got to think ahead just a little bit here. It's easy in math to just kind of blindly stumble along, and I don't mean stumble along, but just kind of try stuff. And sometimes, you just kind of get on the right path, but it's better to try to use a little vision and think ahead here and just kind of think how this whole problem is going to unfold. How am I ultimately going to have to solve this equation, do you think? You guys talk to me about this. I'm talking too much. How's this thing going to play out? Okay, we're going to get a quadratic equation, aren't we? When we do what? I mean, it is quadratic, but you're thinking we're maybe going to get a cleaner quadratic equation when we do what? Okay, so when I expand out the x minus 3 squared, right? So ultimately, what form do we probably want this quadratic equation to take? Standard form, right? ax squared plus bx plus c equals 0, right? I'm just going to push everything to one side. Are there any other options? Now, what about this? When you look at this, could we isolate this x by isolating this and square rooting? What's the problem with that? We got an x, we got another x. We can't do that, can we? Right? So we can't isolate this thing by square rooting because I've got this other term in there. So the only option I have on this thing is just to expand everything out and put it in standard form. Did everybody see that? Okay. All right. So we've talked about. I'm trying to think. We talked about expanding polynomials. There's so many classes going on. It's hard for me to think exactly what we've done in each class. How would we deal with that x minus 3 squared? See if you can do this using a pattern, right? This is the pattern a plus b quantity squared. Okay, so let's try that. Let's see if we can consolidate some steps here. And this is going to seem a little bit weird. And sometimes you probably wonder why I skip steps up here. Well, I don't want to, with an honors class like this, it's really better for you guys to start thinking about doing some mental math, because mental math, if you look at I think I might have mentioned this to you, if you look at a real-time imaging of a person's brain, and you can tell what parts of a person's brain are active when you look at a PET scan by looking at the blood flow, and you see the electrical activity in their brain. You can get a really good idea now with modern brain science what parts of your brain you're using when you think about certain things. And it turns out that when people do algebra or they do mental math, the same parts of their brain are active. You're doing the same mental processes. And so you literally become better at thinking about this stuff if you challenge yourself to do some mental math. You don't want to write down every little tiny step. Okay, so let's see if we can take care of this part right here. We can just think through that. I'm going to distribute the negative to the expansion of x minus 3 squared? Rebecca, you want to tackle that? I think you started to go on that.
It would be difference of squares because you'd end up with 3 squared minus x squared.
Okay, but now if I'm expanding out x minus 3 quantity squared, that's an expansion pattern, right? That's where we got to do a binomial expansion. Let's think just for a second let's remind ourselves real quick, what is that expansion? If I do a plus b squared, how's that go? This was all that Pascal's triangle stuff, remember? But then we want to sort of remember, let's just review the patterns, the two patterns that we want to remember. The cubic expansion and the quadratic expansion, binomial expansion. There's a binomial, and when I say expansion in math, it means we're multiplying it out, okay? So a plus b squared is what? Plus 2ab plus b squared. Okay, and while we're at it, let's try this one. A plus b cubed is a plus, right? 3a squared b plus, good, plus b cubed. Okay, good, right? And if you don't remember that one might be worth making a little flashcard. What I would honestly do, if I could go back in time to high school, one thing I would probably do is assemble just a little Ziploc full of flashcards, all the things in my classes that just a few little, the equivalents of the mathematical state capitals, the things you just got to remember. Quadratic formula. I mean, that one you probably don't, you just remember that when you use it so much, but some of these other things that you use from time to time, that after the summer it would be nice to be able to just sit down for 15 minutes and just go through the flashcards and you know them again. Yes, ma'am. You found it? Oh, send me a link, please. That's what did it, because I looked at some stuff too. I looked at Michael Jackson. I looked at Dancing Baby. I couldn't. That's the one that did. Okay, good. Please send that to me. That's funny. Yeah, please send that to me because I looked and looked for that. Okay, so then what are our A and B going to be here? A is X and B is -3, right? Good. Okay, so when we expand this out then, we're going to get X squared, but I'm distributing this negative, right? So we can kind of think through this. So I'm going to get a negative X squared plus 2 times X times -3 times -1, right? So that's going to be a positive 6x. Everybody buy that? Plus -3 squared is 9 times -1 is a -9. Okay, good. And now this is looking pretty good, right? Now this is starting to look an awful lot like a quadratic equation in standard form. Where do we go from here probably? Combine like terms. We could combine everything on the left and switch the signs. That's fine to do. 6 of one, half a dozen of the other. What I would do personally, not that it's such a big deal, I would probably, in my mind, I would push everything over here just so I get a positive x squared. Does that make sense? So I'm going to end up with then an x squared. I'm going to have a minus 12x. And if I add the 9 over to this side, I'm going to get, what's that, 35? And then I'll just flip the 0 over to the other side, okay? And we ought to be able to find magic numbers. Yeah, we can. So what are my solutions then? What's it factor into? There you go. What are the magic numbers? -7, -5. So I end up with x equals 7 or x equals 5. Boom. Make sense? Okay. It's just a lot of this is on this assignment. It's just going to give you some maybe slightly harder quadratic equations to solve for one thing. But the other part of this assignment is finding convenient, tricky ways to solve these systems. Sure. Oh, yeah, sorry. We didn't finish, did we? No, because we got to, right, I forgot we're solving a system, aren't we? So we've got to take this solution that we got, and that was the solutions 7 and 5. And let's actually, I'm going to throw another page in there. How about? And we'll do the substitutions because this is an important, something important happens here too. I'm going to save this. I feel like this thing's going to crash here any second. Why is it doing that? I don't like that. I'm getting nervous. There we go. I think we got it fixed. There. Okay, and our solutions were 5 and 7, correct? Okay, so now what? We got to solve a system here. I need y values. So what do I do? What do you think, Andrew?
Could you just plug them into that bottom equation and make two different equations and solve for y?
Sure. Yeah, right. So just plug them into either equation,
Yeah.
right, and solve for y. Either one's fine. I might just, like 5 goes into this one pretty easy, actually. 5 minus 3 is 2. Squared is 4. Times 1/4 is 1, right? So this gives us the ordered pair 5, 1. What about 7? That goes into the top one pretty well too, doesn't it? 7 minus 3 is 4. Squared is 16. Times 1/4 is 4. Make sense? Okay. Okay, how about this guy? So here we've got 2 quadratics this time, don't we? Actually, these aren't even quadratics. Do you know what those are? Those are bizarre. Those are going to be like ellipses. Okay? But it doesn't matter. We can solve this thing. How are we going to solve this system? We could use elimination. Everybody see that? Right? Because I can use the principle of linear superposition, which just means that, it's a fancy word, it just means that I can add equations to create another true equation, right? Doesn't that make sense? If this side is equal to this side of the bottom equation, if I add the left part of this bottom equation to the top one and the right part of the bottom one to the top one, it has to be a true statement because both sides are equal. I've added something equal to both sides. Agreed? Okay, so we'll want to use elimination here. What would be the easiest way to use elimination? What would I want to multiply? I'd want to distribute some numbers through both equations. How about the top one? What would I distribute through the top one? Am I going to target the y's or the x's to cancel? The y's, aren't I? And look, I've got like terms there, don't I? I've got y squareds, so I should be able to add those to 0 if I'm smart about it. I'm going to multiply the top one through by what? By 2. Okay, and the bottom one through by 3. Good. And that's going to give me 8x squared minus 6y squared equals negative 22. On the bottom, I'm going to get 15x squared plus 6y squared equals 76. And when I add those up, look, the y squareds cancel. That's good. So I get 23 x squared equals 54. Did I do that right? Oh, yeah, I doubled it, didn't I? Yeah, no wonder. I wasn't working out well. There you go. Thank you. Good thing you caught that. You're right. So it's going to be, what did we say it was, 114? Okay, so that's going to give me then, what, 92? So now what would I do? Yeah, so what's my strategy here to solve that equation, obviously? Just isolate the x, right? I can point to a single x. So we divide by 23. We get x squared equals 4. So what's x equal? Good, plus or minus, because I'm square rooting both sides. Plus or minus 2. And so we get two possibilities here. Either x equals -2 or x equals +2. And all we got to do now is just plug those into one of the two equations and solve, right? I'm going to plug into the bottom one where I'll end up with a positive coefficient of y. Not that it matters very much, right? But if I plug that into the bottom equation, I'm going to get 5 times 4 is 20 plus 2y squared equals 38. And then what are the steps to solve for y there? Subtract 20 and divide by 2. And what's that going to give me? 9. 18 divided by 2 is going to give me 9. So I'm going to get y equals plus or minus 3. Okay, good. And so what's that tell me then? What are the ordered pairs that I got out of that?
-2, 3, and -2, -3.
Everybody see that? When x is -2, I got two y values. So that's giving me two separate ordered pairs, -2, -3, or -2, +3. Okay? What about over here? Same kind of thing, right? If I plug 2 in fact, what's going to happen here? If I plug 2 in to the bottom equation, does anything change? Okay, everybody get that? The bottom equation, we could say, is insensitive to the sign of x. That's how we say that in math, because the x is being squared, right? So whether x is positive or negative, it's not going to change the outcome, is it? When I plug in -2, I'm getting exactly that same equation, right? I'm getting 5 times -2 squared is also 20, plus 2y squared equals 38. So we already know what the outcome is going to be. I'm going to get y is plus or minus 3. So what are the other ordered pairs I get then? Whoops. And 2, +3, right? Okay, does that make sense? What would this thing look like? It's going to end up looking something like this. It's going to be just, I think something like that, where you have these points that line up vertically and they line up horizontally, those points that are the intersections. Okay, something like that probably. Okay, questions? Good. Okay, how about this one? Maybe we don't even have to do the whole thing. We could just, the math is not going to be hard, but we just have to look at our strategy. What would our strategy here be, maybe? Yeah, just probably solve for x and plug it in, right? Solve for x, plug it into the top equation, get my solutions for y, probably two of them, right? Because I'm going to get a quadratic equation, plug each of those back in down here to the other one and find the corresponding x values, right? Okay, probably don't even have to do it. I'm just talking strategies here. Okay, how about this one? Okay, we are eventually going to have to expand that bottom one for sure. Maybe before we even do that, though, can we eliminate a variable here? Everybody see that? How we could eliminate the x's here? We could either substitute if we wanted to. So for example, look what you notice here. One thing you notice that I want you guys to see is that I've got an x squared term there and an x squared term there. So if I want to make a substitution, I don't have to solve for x, do I? Right? I could substitute directly for x squared. Do you see the shortcut? So in this top one, if I solve for x squared, I'm just going to get 4 minus y squared, which I could plug in right there, couldn't I? Right? Right? If you just kind of blindly jump into that, you might be tempted to say, oh, I got to solve for x and then plug it. But that's going to be a mess, isn't it? Solving for x is going to give me positive and negative equations, right? I'm going to get two equations involving y's. I have to make two substitutions. That's way more work than we want to do. Just solve directly. When I see like terms like this, just solve for that like term without breaking it down any further and then make the substitution. So what's that give me then? I'm going to end up with, for that x squared, I would just substitute a 4 minus y squared plus the quantity y minus 1 squared equals 1, right? And now I'd have to expand that thing out and collect like terms and solve from there, wouldn't I? Okay. What else could I have done? I could have just multiplied this top one through by -1 and used elimination also and just added. Everybody see that? Same thing, okay? So what's this going to give me then? 4 minus y squared. If I expand that, would you guys agree that's just going to give me y squared minus 2y plus 1 when I expand that? A squared plus 2ab plus b squared, okay? And look what happens now. We've got these ones cancel. That's good. Look, the y squareds cancel. Let's do it this way. This gets pretty easy, doesn't it? Then I just end up with 4 minus 2y equals 0. Push the 2y to the other side, and I get 2y equals 4. So I get y equals 2. I get a single solution for y. What would I have to do now to solve for x? Plug it in. Where would I plug it in? Okay, but there's a reason I put a box around my substitution equation. See what I'm saying? We can immediately go back to the box because that's going to be the other variable. That's how we can identify it easily when we're solving a system. Okay, so then that gives us x squared equals 4 minus 4, 0. So what's x? We just get 1 point this time. Our solution is just the ordered pair 0, 2. Okay? Good? Okay. So this time we had two circles that intersected tangentially. What this one looks like exactly is something like this. And it's these two circles. And they intersect at the point 0, 2. Okay? Not that that's that big a deal. I just wanted to show you what it looks like. And then finally, what about this one? What could I do here? What could I do? Everybody see that? Right? Or I could either solve for this xy term and substitute, or this time, why not just use elimination? Why not just distribute a negative through this bottom one? And then that's going to give us the two equations, 2x squared plus xy equals 2, and negative x squared minus xy equals 2. add those up and get x squared equals 4. So x equals plus or minus 2. And then I would have to test both of those, wouldn't I? I'd plug those back in. So if I take x equals 2, and let's just use that original bottom equation. If x equals 2, that's going to give me 4 plus 2y equals negative 2. Subtract 4 and divide by 2 and get y equals negative 3, right? So then we get the ordered pair there, negative 2, negative 3. There's one solution. And then I do the same thing over here for negative 2. If x equals negative 2, and we plug that in down here, I'm going to get 4 minus, say it again. Oh, 2, you're right, positive 2. Yep, you're right, positive 2, negative 3. And then here we got 4 minus 2y equals negative 2, so that's going to give me 2y equals 6. So y equals 3. So we get the ordered pair, negative 2, 3. Okay, good? All right, that's it. You can work on this assignment. And then the next topic we'll come back with next week is we're gonna talk about dividing polynomials. How to do divide, and that leads into a lot of really cool stuff that you wouldn't expect.